Okay, good evening. This is Professor David J. De Los Reyes. The date is March 29, 2023. The time is around 10:15 p.m. Professor David J. De Los Reyes. Okay, my topic for tonight will be, it's one of the most exciting problems in advanced mathematics, and this will now be the series connection of a resistance, inductance, and a capacitance energized by the current source, okay? We are asked to find for the current as a function of time by using Laplace transform. Okay, I will check my calendar. Okay, let's proceed. My lesson for tonight will be Advanced Math, lesson number 25. The problem is actually a resistance, inductance, and capacitance connected in series, energized by a direct current source, and by using Laplace transform, we are asked to find current as a function of time. That is by using Laplace transform. The previous solution is actually the so-called classical solution, and that classical solution is actually, what do you call this, differential equation. Okay, let's proceed. The figure of the problem is actually a resistance, inductance, and capacitance. They are all connected in series, energized by a direct current source A. They are connected with lines, and there's a switch over here. And the problem is asking what will be I as a function of time, as a function of resistance, inductance, and capacitance, and the voltage E. What will be I as a function of time? By using Laplace transform. Okay, let's proceed with the solution. Sigma notation, this is voltage, this should be equal to 0. The meaning of this is that the summation of the voltages around this closed loop, as we close the switch, should be equal to 0. Plus E minus B sub R minus B sub L minus B sub C, the summation should be equal to 0. Okay? A plus voltage will be a voltage source, and a negative voltage will be a voltage drop. So this is plus E minus B sub R minus B sub L minus B sub C, and this should be equal to 0. Voltage source, voltage drop, voltage drop, voltage drop. If we take the summation, the sum should be equal to 0. Okay, let's try to bring out the equivalent of B sub R, B sub L, and B sub C. Excuse me. We will transpose all the negative things to the right. So E now, B sub R is actually I, small I times R, and B sub L is actually the inductance of the coil, times the derivative with respect to time of current, the rate of change of current with respect to time. For a coil, the current passing through it will be L di dt, okay? And for the capacitance, we have passed by this already from the previous discussions. It should be 1 over C, the integral of I dt. The integral of I dt is actually the charge, and the charge over the capacitance is actually B sub C. But in terms of the so-called integral formula, it will be 1 over C, the integral of I dt. Okay? What comes out now is a complicated equation. It is an integral differential equation. If from the previous examples, they are only the integral equation and then simply differential equation, for tonight, this is the worst case scenario for an RLC-DC, because the resulting equation is actually an integral differential equation. Why integral differential equation? We got an integral sign here. So some part of the equation is actually an integral equation. We got the di over dt over here, or the derivative with respect to time of I. That's a differential equation. So actually, The summation of this is a combination of an integral differential equation. And by using Laplace transform, okay, we will solve for current as a function of time. Okay, let's proceed with the solution. Take the Laplace transform of all the terms. The Laplace transform of E will be E over S. E is constant. Okay, a constant, the Laplace transform is actually E over S. It should be that constant all over S, equal to the Laplace transform of Ri will be R. I is variable, so it should be the Laplace transform of small letter I will be capital letter I as a function of S. Plus, I will check my camera. Oh, it's still fine. The Laplace transform of L di dt, we have passed by the formula on how to take the Laplace transform of any differential thing, right? So this should be L, it will be S, okay? The variable for the meantime is current, so it should be capital letter I as a function of S, minus small I sub 0 plus the initial condition, close bracket, plus, I am following this, right? 1 over C, the Laplace transform of any integral thing, it will be 1 over S, the variable is actually current, so this should be capital letter I as a function of S. We have passed by this situation from the previous examples, right? Plus 1 over S, I sub 0 plus. Oh, sorry for this one. Just simply 0 plus. There is no 1 over here. Okay? This is actually the given initial conditions. And if we try to simplify this one, I sub 0 plus is 0. I sub 0 plus on the capacitor is also 0. So if these two here are 0, the resulting equation now will be E over S, R, capital letter I as a function of S, plus LS, okay, with the product of L times S, S, times I as a function of S. This is now 0, right? Got no more effect. The product of 1 over C times 1 over S is 1 over CS times I as a function of S. This is 0 really. Okay? There is a common factor, capital letter I as a function of S, right? We factor out, open bracket. The first coefficient should be R. The next coefficient should be LS. And the third coefficient will be 1 over CS. Close bracket should be equal to, I just rearrange, right? I put this on the right, I put this one on the left. It's the same, so it will be equal to E over S. Okay? I, capital letter S, will simplify this one, the one inside the bracket. Because there is a fraction over here, and there is no fraction. These are R over 1 and LS over 1. So if we try to simplify the one inside the bracket, we will multiply R and LS by this denominator here. So R times CS will be RCS. LS times CS will be, what comes out? LC, S times S will be S squared, plus 1, all over, okay, we are combining the three terms inside, all over CS. Because if we try to simplify this one here, RCS divided by CS is actually R, and LS divided by CS is actually, or LCS squared divided by CS will just be simply S. But we could compress this as simply RCS plus LCS squared plus 1 all over CS, and this should be equal to E over S. And luckily, this S here cancel with this, right? Then we will multiply all the terms by, we want to eliminate this, okay, multiplied by C, right? So the left hand side multiplied by C, this C here cancel with this. So this is just the coefficient remaining on the left. should be equal to the product of E times C will be CE, right? Then again, we will divide both the left and right by this coefficient here. So I as a function of this now will be CE. This will now be CE, right? CE all over this. That is LCS squared plus RCS plus 1. Okay? Okay, let's try to factor out. We will factor out the 1 on the denominator. There's a reason behind that. Because we would like that the resulting equation will be S plus A plus 1 over S plus B. This is a quadratic equation. So there are two possible factors of this one, or roots actually. It could be an A plus B over here, but we must have to compute for the value of A and B. So if we try to factor out, I will erase this one. LCS squared plus RCS plus 1 equal to 0. It's a quadratic equation. L is constant, C is constant, the product of two constants will be constant, and that is referred to as the coefficient of S squared. So the coefficient A for a quadratic equation is LC. Okay? For the S thing, resistance is constant, capacitance is constant, the product of two constants will still be constant, so the product RC refers to the coefficient B should be equal to RC for the quadratic equation. And the pure constant term, this is actually the pure C. And C should be equal to 1. So by using the quadratic equation, we are solving for S in terms of, solving for S, right? S now will be negative B plus or minus a square root of B squared minus 4AC all over 2A. So if we try to substitute, what will come out? B is actually RC, right? But it should be negative. Plus or minus the square root. B squared is RC quantity square minus 4 times A, which is LC, and the value of C is actually 1, all over 2A. So 2 times the product of A, which is LC. I put the simplification over here. I tried to divide this RC here, divided by this. Okay? I distribute. So RC over 2LC will be R over 2L. So this is now negative R over 2L. Right? Then the remaining 2LC, I will put inside the radical. So if I will put them inside the radical, I will square 2, it will become 4. I will square L, so it will become L square. I will square C, so it will become C square. So if we try to simplify the terms inside the radical, what will come out? R square C square over 4L square C square minus, I'm following this, 4LC all over 4LC square, or it can be written as 4LC times LC. And actually, the simplification is R over 2L quantity square minus 1 over LC. This 4LC here, cancel with this. Right? So this will remain 1. So 1 over LC. And this one, if we try to simplify, this C square cancels out. So no more C square. Okay? And R square is a perfect square. 2 is a perfect square. L square is a perfect square. So it can be written as R over 2L quantity square. Because if we try to square this one, what comes out will be R square over 4L square. It is this. And this is minus 1 over MC. So capital letter I as a function of S should be equal to, I will go back here, CE, okay, times this equivalent over here. Okay. This equivalent from the resulting one is actually 1 over S plus alpha plus beta plus 1 over S alpha minus beta. where the value alpha is actually the first root. If we consider the positive side, alpha is actually minus r over 2l, okay? And the value of beta is the total value of the square root. So actually, this one here, excuse me, this can be written as CE, CE times the equivalent of this. It should be 1 over S plus alpha plus beta plus 1 over S alpha minus beta. Right? This is one. Okay, so upon reaching this one, we will take the inverse Laplace. The inverse Laplace transform of capital letter I as a function of S is small letter I. We rewrite CE, so this CE. S plus alpha plus beta is similar to 1 over S plus A, right? And under Laplace, it should be e raised to AT. So there are actually two exponential equations that will come out. The equivalent of this, if we try to take the inverse Laplace, it will be e raised to negative open quantity alpha plus beta t plus a raised to negative a again. But the sign of the second part will be negative because we are taking the second value. Okay? Exponential function, exponential function. So if we try to simplify this one, we will just let CE to be k. So I now will be k e raised to. The Laplace equivalent is actually exponential, right? So a raised to AT minus AT, a raised to minus AT. This is the first, what you call the exponent. This is second exponent. This is minus, this plus. So they are different. So the final equation now is actually k a raised to negative open quantity negative alpha plus beta times time, a raised to negative alpha minus beta times time. Okay, that's the general solution. Okay, so for the three cases now, under RLC-DC, there are three cases. If the value inside the radical sign, if R over 2L quantity square is greater than 1 over LC, S1 and S2 are real and unequal, and this is the resulting solution. See? The circuit is said to be so-called overdone. Okay, it seems it cannot go to the so-called oscillatory condition, overdone. For case number 2, if the value of the terms inside the radical sign, that is R over 2L quantity square, is equal to 1 over LC, S1 and S2 will be real and they are equal. Because for the second case, the one inside are equal, so this is God, right? So S1 and S2 are real and equal, so the solution now will be this. Right? And the circuit is said to be so-called critically done. For case number 3, if the ratio R over 2L quantity square is less than 1 over LC, S1 and S2 are complex conjugates. They are complex numbers and they are complex conjugates, meaning the other is plus the imaginary part. The second one is actually a minus. Complex conjugates. So actually S1 is equal to alpha plus J beta and S2 is equal to alpha minus J beta. They are complex conjugates, but they should be plus is minus, so we could see it as they are simply complex conjugates. And the solution for case number 3, if we try to follow this, and by using the Euler's equation after the simplification, I now will be a raised to alpha t times open quantity k1 cosine of beta t plus k2 sine of beta t, okay, closed quantity. So these are the three I as a function of time for RLC-DC. Okay, case number 1, this is the current. Case number 2, this is the current. And case number 3, this is the current. Overdone, critically damped, and this is oscillatory, meaning the current is oscillating. Okay, that's it, guys. Actually, the solution is much simpler than the so-called differential equation. Because only upon reaching this one, we try to take the equivalent of this, okay, or we'll find the roots for s by using a quadratic equation, okay? And according to our quadratic equation, the possible roots are actually alpha and beta. And for alpha and beta, there could come out three possible cases, that is case number 1, case number 2, and case number 3. Okay, that's it, guys. So for those people who are taking advanced mathematics, this is for you guys. If you want to subscribe to my channel is at youtube.com/@prof.davidj.de. And if you want to share it, please click share. This is the solution of a series RLC-DC, okay, using Laplace transform. Good evening from Los Angeles.